Hello everyone, welcome to my calculus lecture. In this lecture, we study implicit differentiation. So what is implicit differentiation about? Before we talk about that, let us first talk about implicit functions. So far, most of time, we have seen functions defined by y equals f of x. But often, functions can be defined implicitly. What do I mean by that? For example, let us consider x squared plus y squared equals 25, where you can easily see that this is in fact the equation of a circle centered at the origin with radius 5, right? And as you know, of course, circles are not functions. However, it can be a function, like this guy can be a function with the constraint y, is greater than or equal to 0. In that case, it represents the upper half circle, which can be given by the equation y equals the square root of 25 minus x squared. So functions defined by equations like x squared plus y squared equals 25 are called implicit functions. Note that, however, not every implicit function can be written in the form y equals f of x. For example, x cubed plus y cubed equals 6xy, right? This is one of those kind. Okay, one of those kinds. Hence, we need to devise a way to differentiate an implicit function without writing it as y equals f of x. That's what we call implicit differentiation. So how does that work? It turns out that implicit differentiation is none other than the chain rule. Okay, so in fact, there is nothing new. It is the chain rule with the assumption that y is a function of x. Just like in the previous example, right? X squared plus y squared equals 25, right? So when you just look at the function, we don't know whether it is a function of so we don't know actually y is a function of x, right? Okay, so it is implicit, right? But once you assume that it is so y is a function of x, right, by imposing the condition that y is greater than or equal to 0, okay, which we represent the upper half circle, okay. So in that case, it is a function, right? So, so y is a function of x, right? So here is an example. So we have a function y to the power n, and here also we are assuming that it is a function of x. So we actually find the derivative of y to the power n with respect to x. So in this case, the y itself it works as the function u. Remember, right? When we studied the chain rule, right? We introduced the variable u, right? So in that case, the y is actually u. So by the chain rule, the derivative is what? First, you take the derivative of y to the power n with respect to y. So that is denoted by y to the power n prime. And then you will have to multiply that by dy by dx. So we get n times y to the n minus 1 times dy by dx, right? So that's the the implicit differentiation, but it's nothing other than none other than the chain rule itself, right? With the assumption that y is a function of x. Okay, so it's no big deal. By the way, this guy here, derivative of y to the power n, also appears so often. Although this is an example, but at the same time, you might want to consider this as a formula, okay, important formula that you would like to remember, okay. Okay, next example, the derivative of cosine of y, but we are not taking derivative of this function here, cosine of y with respect to y, but we are taking the derivative of cosine of y with respect to x variable by assuming that y is a function of x. Okay? So again, by the chain rule. So in this case, y is like a u. Okay? So the innermost function here, right? So the first, you take the derivative of cosine y with respect to y. So which is, represented as cosine of y prime. You have to multiply that by dy by dx, by the chain rule. So that is negative sine y times dy by dx, okay? So, when we studied the chain rule, in the end, I told you to rewrite u as a function of x, right? But in this case, the only thing we know is y is a function of x, but we don't know y is exactly, right? And in many cases, when it comes to implicit functions, right, often you can't solve it for y. So that's why we are going to just leave it like this, sine of y. Okay, so let's talk about the following examples. Okay, so first example is find y prime if y satisfies the equation x cubed plus y cubed equals 6xy. Again, this is an implicit function which cannot be written as an explicit function like y equals f of x, okay? Right, so we are going to use the implicit differentiation, in other words, the chain rule. And then next question is find the tangent to, so here find the tangent means the equation of a tangent line to this curve x cubed plus y cubed equals 6xy at the point 3, 3, okay? Right, so to work on those examples, example problems, we gotta go to my notepad. Okay, so here's the example. So first the equation is, first question is find y prime if x cubed plus y cubed equals 6xy. So let us work on this first solution. So really, all you have to do is to differentiate this equation with respect to x by assuming that, the y is a function of x, right? So we have 3x squared plus y is a function of x. So if you take the derivative of y cubed with respect to x, remember, the earlier we calculated this, right? The, this is important, so I'm going to use a box, okay? This guy. derivative of y to the power n with respect to x, right? That's, you don't actually, have to memorize this, as long as you know how to do the derivative, but that's n times y to the power n minus 1 dy by dx. Okay, dy by dx. Okay, so that's going to be 3y squared dy by dx. Right hand side, so first you take the derivative of x, that leaves 6y. I'm doing the product rule, right? And then 6x times derivative of y is dy by dx. Okay, so as far as like implicit differentiation is concerned, we are done. But we have to get dy by dx, right? So here, there are two terms. And the left-hand side, we have this one that contains dy by dx. And the right-hand side, we have this guy, which contains dy by dx. So we got to put them together so that we can solve it for dy by dx, right? So I'm going to subtract the 6y from each side. So we get 3x squared minus 6y on the left-hand side. And I'm going to subtract this guy here from each side. So, and then factor 6 dy by dx. We get 6x minus 3y squared times dy by dx. Okay, that's simple algebra. And then now we are going to divide each side by 6x minus 3y squared. That way we can solve this whole equation by dy by dx. So that equals 3x squared minus 6y all over 6x minus 3y squared. Okay, so we found it. That's dy by dx. Again, this is an implicit function, right? In this case, we can't solve it for y, so you can't have, dy dx as, the function of x, okay, explicitly. So this is the best we can write down. Now moving to next question. So what was that? That was find the tangent. Find the tangent to x cubed plus y cubed equals 6xy at what point? At 3, 3. Okay, first let's check that this point. I mean, that's obvious, but I still want to check though. So first let's check that 3, 3 is actually on this curve, right? So how do you show? Well, plug in x equals 0, x equals 3, y equals 3, and the left hand side and also right hand side, and then they must coincide, right? So that way we can confirm that 3, 3, the ordered pair, or x equals 3, y equals 3, that the point is actually on the curve, on this curve. So in fact, if you plug in x equals 3, y equals 3, left-hand side, 3 cubed is 27. So 27 plus 27, that's 54, right? And the right-hand side, x equals 3, y equals 3. So 6 times 3 times 3, 6 times 9, that's 54. So, they coincide. So we confirmed that 3, comma 3, that's this point is actually on this curve, okay? Uh, this satisfies the, the equation. Okay, so the equation of tangent line, in this case is given by y minus y1, 3, and slope, the slope is going to be dy dx evaluated at x equals 3, y equals 3, right? And then times x minus x1, which is 3. So that's the equation. So all you have to do is to calculate the slope, right? So here the slope is dy by dx evaluated at x equals 3, y equals 3. So dy by dx, we found it earlier, right? In the part 1. So that's 3x squared minus 6y all over 6x minus 3y squared. Oh, actually, you know what? We could have simplified this, right? Because the numerator and the denominator have what? Common factor 3. So if you divide the top and bottom by, the 3, we have x squared minus 2y all over 2x minus y squared. Okay, so that's better. Okay, that's better. Right, so we have x squared minus 2y all over 2x minus y squared. And then we are going to evaluate this at x equals 3, y equals 3. Okay, so that's going to be, the 3 squared, which is 9. So 9 minus 6 over 6 minus 9. Well, you don't even have to calculate this, right? Because, you can easily see that this is negative 1. In fact, that's going to be 3 divided by negative 3, right? So that's negative 1, right? So you didn't even have to get here, right? Since the x and y coordinates are the same, so that you can easily see that this is going to be negative 1. Anyway, the slope is negative 1. So the equation of a tangent line is going to be y minus 3 times equals to negative 1 times x minus 3. So if you solve this for slope intercept form, right? So y equals negative x, negative positive 3. So if you move negative 3 over, that becomes plus 6, right? So that's going to be the answer, right? So the equation of a tangent line to this curve at 3 comma 3 is going to be y equals negative x plus 6. Okay, folks, more details of my discussion in this lecture can be found in my lecture note at the following address, right? As usual, this address is hyperlinked. So, all you have to do is click on this address and that will take you to the lecture note. And also, as usual, if you want to go to my main, the blogger site where you can find the other lecture notes, you just need to click on this word blogger, which is also hyperlinked. Thank you all very much for watching and listening my lecture. I'll see you next time. Bye-bye.